Hello. Hello everyone, am I audible? Can one of you confirm if I'm audible?
Yes, sir, yes.
Okay. So before we start the class, I have uploaded a small homework 2, that's based on some basic ideas on OFDM length, sampling rates and other things, and time domain structure for 5G NR and SSB. I gave a week sum. It's a very simple assignment. I mean, it's just looking at the spec and writing things up. Not too much computation or anything is there. So I think I gave up about 8 days. So I request you to everyone to start looking at that and try to complete it. Okay. So today we'll continue with where we have left last time. Just 1 minute. Hold on. Okay. So we were looking at SS block, synchronization block, and we saw the time indices. Actually, last class what we saw was we saw this table and we looked at the time indices, the symbols in which SS block is transmitted. Okay, that's what we looked at last class. Okay, so today we look at the frequency domain location, and then we'll also look at the contents of MIB and how we can use all of this to do the time and the frequency localization. Okay. So where were we last class? We were here, yes. Okay. So as I was mentioning, SS burst is nothing but a collection of SS blocks in a half frame. I mean, this is a very colloquial terminology in the sense that this is not there in the spec, but people generally refer to it as SS burst. Okay. And this is the periodicities that are allowed are 5 microseconds, 10 microseconds, 20, 40, 80, and 160. Okay. And the default periodicity is for initial cell set, the UV assumes that at 20 milliseconds, if it just waits every 20 milliseconds, at some point you will get it. Okay, and we also saw the maximum number of SS blocks for a burst. This is what we know. This is the same thing that I have mentioned. So now let's look at the frequency location. Okay. So when we were looking at the channel raster in the previous classes, what we said was there's a point A, that's a reference point, and there's something called offset to point A, to which SS blocks.
Sir, can you explain the previous slide again, the timing part?
The timing part, huh? Okay.
Of SSB, yeah, please, sir.
Just okay. Okay. So if you look at this thing, so each subcarrier spacing and each frequency range has different symbols in which the the SS block is there. Okay, so let's just let SS block is there, and you understand that SS burst happens in a half frame. Every other half frame it happens. It is located in a half frame. Okay, half frame is 5 milliseconds. Half frame is 5 milliseconds. Yes. Okay. So if you say, and what happens is, let me just open up my iPad. I will just draw it on it and share with you. Okay. So what they do is, so let's just take the example of 30 kilohertz. 30 kilohertz SCS, so that it's easy. Okay. 30 kilohertz SCS. So every subframe has 2 slots. Okay, so this is slot 0, slot 1. So in each half frame, how many slots will be there? About 10 slots will be there. Okay, up to slot 10. Okay. So what they do is they number all the OFDM in the slot in the half frame beginning at this. Okay, so this has 0, 1, 2 up to 13 OFDM symbols, 14 to 27 here. Next is 28 to so on. in the last 139. Okay? Because 14 OFDM symbols are there and 10 slots are there. So for 140 OFDM symbols are there. Okay. So the OFDM symbols are numbered with respect to the half frame. Okay. So the next half frame again they start at 0. Okay. Is this clear? Is this part clear?
Yes.
Okay. So then what they say is, then they give the formula from where which OFDM symbol does the SS block start. Okay. So for example, in case A, it is, let me just copy this and I will explain you. N is equal to 0, 1, 2, 3. Okay. So let's look at case C, 30 kilohertz. Let's look at the 3.5 gigahertz and unpaired spectrum. Okay, that's the TD spectrum. Okay, let's just look at that. Okay, so this is the formula: 2,8 plus 14n and 0, 1, 2, 3. Okay, so this is the OFDM symbol number it gives. So the first position will be, first you put n is equal to 0. If you put n is equal to 0, you get essentially the SS block will start at 2 second OFDM symbol and the second SS block will start. So let's put the index of the SS block. So the index of the 0th SS block, first SS block, 2, 3, 4, 5, 6, 7, 8. This is the index of the SS block. And down and right, the OFDM symbol it starts with. So first you put 0, you get the second OFDM symbol it starts, 8. Okay. Then you add 14 to that, so you get 16 and sorry. 8 plus 14 is how much? 22. Okay. And so on and so forth. Okay, so if you look at this, 2,8, the second OFDM symbol is in the first slot, the 8th and the 8th OFDM symbol is also in the 0th slot. Okay, and the next two correspond to the next slot. Okay, so the first 0 to 7. So these correspond to the first 4 OFDM slots. Okay, so that is how you number the what do you say? The number the SS blocks. Okay. So in the second OFDM symbol, 8th OFDM symbol, there's one SS block here, there's one SS block here, one SS block here. These are possible locations. Okay? You don't have to put them everywhere. And you observe that each SS block occupies 4 OFDM symbols.
So in 30 kilohertz, the slot size will be of 0.5 millisecond, right?
0.5 milliseconds, yes.
So that means we'll have 10 slots in half frame.
Yeah, that is 5 milliseconds, exactly.
10, okay. And then this SS block can be located in any of the slots depending upon the requirement.
Any of this one, no, the slot, that's what I'm saying. It's given in terms of the OFDM numbers. So
yeah, that's okay. I got the point. So basically it is second and 8th symbol of every...
Of the 0, 1, 2, 3, only 3. Yeah. First 4 slots are allowed.
Okay.
First slots cannot have this. Yeah.
So only in the first 4 slot, and then it will repeat after say 20 millisecond, right?
That's we can configure.
Okay.
Okay. So that is the configuration part where you can say that you can configure it up to 5 milliseconds. That is first one half frame in 5 milliseconds means every half frame. 10 milliseconds means every other half frame. Every 4th half frame. So on and so forth.
Okay, so that means you can define how many SS block you want depending upon requirement, right?
Yes. So for example, if you take MS10, I'll show you my screen again. So if you take MS10, essentially this is the first subframe, first half frame, second half frame, third half frame, fourth half frame. So essentially SSB would be present in this. Okay, again in this. Okay, if you take MS20, essentially SS block would be there, SS block would be there here and
in the last.
In the last.
So these are the configuration kind of, right?
So the configuration that are allowed.
So what are the criteria to take more number of SS block?
Okay, so essentially, and of course, millimeter wave systems, it depending upon your users and other things. SS block helps. See, SS block helps in resynchronization. Okay, mainly for resynchronization also. So if you have things, if you have small cells and other things where you are moving around from one cell to another, having more SS block helps.
So is it also related to control plane latency, where is from idle to active? because unless it is synchronizes, it may not start data. So
yeah, idle to active, sometimes what happens is there are two things in it. So sometimes it uses the previous synchronization, it maintains synchronization. Sometimes
okay.
it goes for a resync. When it goes for a resync, essentially, as you rightly mentioned out, this delay will add to that.
Okay. So
Okay.
that's why to maintain the latency, more number of SS block would be preferable.
Will be preferable, but you're wasting resources.
Yeah, in case latency is the prime requirement, perhaps more number of.
Perhaps more number of things. Maybe doing MS5 would be best.
Yeah, and if it is an EMBB requirement, then less number of SS block also be okay.
That one, and also mobility also you have to see.
Okay, right.
Yeah,
Achha.
I mean, basically these are also used for measurements. Later I will tell you this thing. Okay.
Okay,
So
okay,
both
right.
these things play a role.
So in mobility, you require more SSB or less SSB? I feel more.
Mobility, I mean, see, essentially the more, I mean, if you have, but this is okay. I mean, you won't go so fast. But
That's
having more SSB will help you out because you can
right,
do this.
right. Okay, thank you for explaining this. Thanks.
Any other question before we proceed? Okay. So let's go to the frequency. So until now, we were looking at the time, where they are putting in a time. Okay, which OFDM symbol locations and other things. Okay. So now let's go to frequency and understand what is how they place it in the frequency. Okay. So one of the first things is so when we were learning the channel raster itself. So when we are learning the channel raster itself, what we said was there's something called an offset to point A that is given by NCRBSS, the CRB corresponding to SSB. And what happens is this gives you the boundary of one CRB, common resource block. Okay, and from there is something called KSSB, which allows you to do a little bit fine granularity and place your SS block. So given the location of NSSB, CRB and KSSB, you will be able to find the relation of SS block with respect to point A. Okay, so point A plus offset to point A plus KSSB is the SS block. Okay, so this offset to point A comes in the MIB. We'll look at the MIB today. Okay, we'll look at the MIB, master information block. This KSSB is a little bit complicated. Okay, so this KSSB for 15 and 30 kilohertz, it is 5 bits. So KSSB, so if you look at the spec, and just look at this, I'll show you the spec. Okay, so just let's look at the spec one. Right? I hope you can see this. Okay, so for SS block type, okay, KSSB can take values from 0 to 23. With the quantities KSSB expressed in terms of 15 kilohertz. Okay, so every integer is one increment of 15 kilohertz. Okay, whereas for 3,4 type B, which is the type B SSB, what they are saying is 60 kilohertz subcarrier spacing. So 0,11 is used. Okay, to represent KSSB. So essentially KSSB in terms of what it says is a more fine granularity tuning, where you can it's in the boundary of a resource element. Okay, because it's given by 60 kilohertz subcarrier spacing, whereas this offset to point A is on the boundary of a resource block, of a common resource block. Okay, that's what happens. So this is what I was putting here. Sorry, I should have shown you this. Okay, so one thing that you should remember is SSB is a single port transmission. What that means is you cannot transmit SSB in multiple layers. Okay, SSB is a single port transmission. You can do beamforming, you can do all that. I mean, that's outside the scope of the spec. But technically, it's a single port transmission. You can think of this as a single antenna transmission effectively. So effectively, you will not have beamforming gain unless you explicitly do beamforming. Okay, the spec does not provide anything. It does not go through multiple layers. Okay, that's something that you should remember. Okay, and another thing that another thing that they're saying is the same cyclic prefix and subcarrier spacing is used for the entire SS block. Okay, so there's no difference in that. Okay, so now the next question is, on the SSB raster, the frequency synchronization raster. I think last time we just started on this episode. Okay, on the frequency raster, as I was telling you earlier, you have a different synchronization raster compared to the channel frequency raster in 5G NR. And you see that they have different higher level of granularity. For example, for the 3.5 gigahertz, I mean, in the 3003 gigahertz to 24 gigahertz, the synchronization raster goes by increment of 1.44 megahertz. Okay, and what they say is the synchronization raster, the point you select on the synchronization raster is mapped to the center point of the SSB, 120th RE of the SSB. Okay, you remember SSB has 240 REs, no? 240 REs, so it's mapped to the center point. 120th RE is mapped to the synchronization raster. The center of the 120th RE will be mapped to the synchronization raster. Okay, a synchronization raster is given, I mean, it's there for different operating bands. It's provided here along with the subcarrier SS block subcarrier spacing. Right? I'm not very sure on what happens when you have two different subcarrier spacings for a given SS block. Maybe they check both of them, case A, I mean, they're different cases, case D, case E, but I have to figure out, I mean, how does the receiver do? Does it do a blind decoding, or is there something else that we are missing? Okay, that I'll try to find out. Okay, so, but the point that you should take from here is that there's a separate synchronization raster, and the synchronization raster is mapped to the center of the SSB. Fine, does it make sense? Okay, so let's take a particular example. Okay, and then just let's do that. So I was looking at a center frequency of 3.5 gigahertz. Okay, so center frequency of 3.5 gigahertz, I want to map it to the SSB raster. So essentially, from the actual channel raster, it turns out that the closest channel raster point is 350.01 megahertz. Okay, and if I look at the GSCN, which is the synchronization raster, it turns out to be 3.50256 gigahertz. Okay, so there's 85 RE difference between the center frequency and the SS block raster. Okay, so I mean, you can do this calculation. I mean, I just sat down and did this calculation, and you can see at what GSCN does it map to, or what is the closest GSCN that maps to this frequency. Okay, for this particular case, it turns out to be 7848. Okay. Okay. Yes, I think we can skip this slide. The same thing I was just telling you. Okay. Okay. So until now we were talking about SS block. So once you log onto the SS block to the SS block, so by decoding SSS and PSS, what do we achieve? Okay. One thing is, of course, we know at this point, we know the SS block subcarrier spacing, either through decoding or through the specification, the band in which you are. Okay. And we also know the frequency location of the start of the SS block. That's something because of SSS synchronization and PSS synchronization, you can get that. Okay. And we also know the timing location. How do you know the timing location? Timing location, you do not know exactly, you know roughly. You know the OFDM symbol number in which you are. Yes, you know the OFDM symbol number in which you are. Okay, I mean, actually at this point, you won't know the OFDM symbol number you are, which you are in. You know that you are in one of these OFDM symbols, 2, 8 plus 14. For example, you know that you are there in one of these OFDM symbols. Okay, and you know the slot number. You know the slot number also again with ambiguity. You don't know the exact slot number because you don't know the OFDM symbol number exactly. Okay, and of course you know the cell ID. So once you log onto the SSS and PSS, these are the 4 things you know. Of course, the timing location is still not clear. You don't know which half frame you are. You don't know all those details. That will you know only when you decode the MID. Okay, but we'll do that in a minute.
So
okay.
Can I have one?
Yes,
can I have one question? So if I switch on my mobile for the first time,
yes,
my mobile will not have any knowledge of which frequency band the base station or G node B is transmitting. So the synchronization raster will start from which band? How it determines?
I think I'm also not very clear about this. I think your SIM card will have some information, sir. Each carrier will provide some information on roughly the band they are. Okay, I think then what will happen is your mobile phone will start searching those bands, And once, I mean, it will have a band mapping, band table mapping to the SS block subcarrier space mapping. I mean, that's a straightforward mapping. Okay. I think from there, that is how they find out. They move across the raster and find out.
So if the mobile device supports n number of band, it will start searching first band, second band, third band, and so on, right?
Yeah, they have some something called PLM and ID. Also, they have some priority list for that. I'm not very conversant in that. I think they have some priority list for that too, and based on the priority list, they search.
Okay, so for time being, we can think that it searches onto the bands which it supports, right?
Yeah, which it supports. Yeah, I think that's okay from our side. The exact mechanism, I think there's a lot of stuff that happens in the SIM. I'm not very familiar with that.
Right.
So if any one of you knows about the SIM also, maybe you can add a little bit of this material into the classroom. It will be nice. Actually, what happens? I mean, I really don't know what happens what is there in the SIM. That's a big topic by itself.
Sir, as far as I know, the SIM will not contain that band-related information.
Band-related, okay.
Yeah, because I had worked in creating SIM for CDM and GSM in initial days, so it is different configuration, not the band.
But then again, I'm very surprised that they'll search all the bands before they lock on, because it's not searching the band and locking on, but then after authentication again you have to go back and research it. Yes, suppose 5G is supported by both Airtel and Jio. You switch on your phone, your band will start with you are a Jio customer, but you logged on to Airtel, then you will have to get out and then again go back to Reliance, no?
Yeah, that's why it searches one by one. That is called auto search or manual search. And if you go to the manual, it shows all and then
all the configurations. Yes, yeah, it actually shows all.
Sir, sorry to interrupt here. Can it recall the last latch frequency before switch off? Something like that? No.
Sometimes it does, but first time you switch on freshly, that's what happens. That's what we're trying to discuss. Yeah, once you switch on, you can have information that maybe you can store in the volatile non-volatile memory of the SIM or something, saying that okay, I have logged onto this band, so it fastly switches on. So, for example, when you go to a different country and switch on your phone, it will do some scan. It will try to find out all the operators, and then something happens. I am not very sure. And then, of course, it's a higher layer thing, I guess so. Then more and more. Okay, I'll try to find out on this. I mean, it has something to do with PLM and IDs and other things. I'll try to find that out. Okay. So, is this part clear? You understood what when we block onto SSS and PSS? I think this is what we have. Okay, time still there's an ambiguity in the time symbol that you are in. Okay, so let's figure out how that is handled. Okay, to handle that, we require to understand what is the information that is there in PBCH. Okay, so if you look at SS block. So until now we were focusing only on PSS, SSS. Okay, but SS block also has PBCH, which are decodable information. These are bits. Okay, so now let us understand what is there. What is the information that is stored in this PBCH? Okay, the information that is stored in PBCH is called the master information block. In short, MIB, master information block. Okay, in addition to master information block, there's a little bit more information. We'll look at that. So MIB is there in SS block. You now look at that part. Okay. So the first thing to understand is, so now you logged on to one of the, so let me just open up my iPad so that we can discuss. Okay. Suppose, okay, you switched on your phone and you logged on to this SSB. Okay, you logged on to this SSB. So you know the frequency content. You know that you're logged on to some OFDM symbol, but you don't know which OFDM symbol it is. Okay, so to identify the OFDM symbol that you logged on to is if the SS block has some information about the SS block index. Suppose you are able to suppose SS block tells you this index, which is 2. You'll be immediately able to understand that it is 16. The location will be 16. 16th OFDM symbol is what you locked on. Once you know it's 16th OFDM symbol, you know which slot number it is and the relative relative location to the slot beginning. Okay. So the first thing is to identify which index, which SSB index it is. Okay. So the SSB index information is transmitted partly in MIB and partly it is spread over the other parts of SS block. Okay, so that's what we are trying to understand. So how do you find this SS block index? Okay, is this problem clear?
Yeah, so is MIB part of SSB itself?
Yeah, MIB is the information that is stored in the PBCH of SS block. MIB is the information that is stored in the PBCH.
Okay, here. Okay.
Okay. So SS block is PSS, SSS, MIB plus some other little bit more information. I will show you that.
And SIB is not here, right?
SIB is the next one. Secondary information block comes in CORS at 0, which is the next one what we'll do. After you decode MIB, you decode that one. Okay, that's not part of SS block. Okay. So the first thing that happens is this ISSB. So what they do is they encode this information, this index of the with the SSB index in very weird manner. Okay. So how do they encode that information is what I'm going to say. So if you look at L, this is the maximum L that is possible. Yes, now. So for less than 3 gigahertz, you require only 2 bits. Okay. For less than from 3 to 6 gigahertz, you require 3 bits to indicate which L you logged on to. Okay. And for greater than 6 gigahertz, you require 8 bits. Does it make sense? So you require 3. So what they do is, what they say in the specification is, one minute, I'll tell you. This is not.
So L here you're talking about location?
L is the index, SSB index.
Okay.
L is the SSB index. So that's what I'm trying to say. When you get the information about the SSB index, you know the OFDM symbol location in which you are. Yes?
Right.
So that is what they try to do. So see, this is the thing that you should read. Whatever I highlighted. The candidate SS blocks in a half frame are indexed in ascending order from 0 to L max minus 1. Okay. A UE determines the 2 least significant bits for L max equal to 4 or 3 least significant bits for L max greater than 4 from a 1-to-1 mapping with respect by using the DMRS sequence that is transmitted. Okay. So using the specific DMRS sequence that is transmitted, they try to find out the index for what do you say, the bits, the index of the SS block. Okay, so let me explain you that in a minute. Let me explain. Let's just go back and understand this. Okay, so remember, this corresponds to 2 bits. This corresponds to 3 bits. So any index for between 3 and 6 gigahertz can be disturbed by 3 bits. This is
6 bits, huh?
how many bits we require? 2 power 6. No, sorry.
6.
Sorry, not really. Sorry. Okay. So what they do is, this is what they do. This is one of the weirdness of 5GNR. So they use pilots to decode this. To pilots, they encode this information in the pilots. How they encode this information in the pilots is, see, essentially PBCH has pilots. We saw this PBCH, and this PBCH has pilots. All around the place they have pilots. The pilot locations are also given here. These are the DMRS pilots. Okay, these are the demodulation reference signal pilots. Okay, so you have to first decode this web. You have to first get the location of these pilots. Once you get the location of the pilots, then you use these pilots to do channel estimation and other things. Okay, but they also encode this information in the random seed in the pilots. Okay, so for example, what they do is the C to M. So if the pilots are QPSK modulated, you can see that they're QPSK. The C of M is nothing but a binary sequence. Okay, it's a specific binary sequence. We'll look at this more in detail. That is generated by a random seed called C init. Okay, so what I'm trying to say is C of M is a binary sequence, 0-1 sequence that is generated by this random seed. By this seed. Okay, so you give a specific value of C init, you get a different sequence. Okay, so this C init is a function of, if you look at the C init, it's a function of the cell ID. It's also a function of ISSB bar. Okay, so let's look at this ISSB bar for here. So what is ISSB bar? ISSB bar is equal to ISSB let's just go look at the L max equal to 8 case, so it's easy. L max equal to 8 case is the least 3 significant bits of the SSB index L. Okay, so what that means is, let's get back to this part. Okay, suppose in this case 2 is the second. Suppose I'm transmitting this BPCH. This is the PBCH. For this PBCH information, my L will be equal to 2. Okay, so my last 2 bits are 1 0. 0 1 0 is my last 3 bits. Okay, so 3 bits are sufficient. What they do is, this L equal to 2 is now becomes ISSB. Okay, ISSB is now 2. Okay, so they generate this random seed by using that ISS. I mean, using this L. Okay, and then they transmit it. Okay, so the receiver, what do? What you do is you extract this DMRS and then try to regenerate the try to correlate with the locally generated DMRS by using different CNITs. For example, what you do is you try to, you give different values of ISSBs and see which correlates the best. And from there you obtain what is the ISSB, and from once you get ISSB, you will obtain the 3 least significant bits of the index cell. When you have L max equal to 8, that is the index. If it's not, if it's, for example, if 64, I'll tell you where you get the other 3 bits. The other 3 bits you get from somewhere else.
Excuse me, sir.
Yes, please.
So this pilot, everything happens at the BTS side, na, sir?
Pilots are transmitted by the BTS. Yes, exactly.
So then why you're taking index 2, sir? Because for the BTS, all will be, I think.
Yeah. Okay, so essentially, that's actually a very good question. So I'm transmitting SS block. Sorry, I'm transmitting SS block here, and other things. Now, the SS block information here is different from the SS block information here. Okay, the PSS and SSS remain the same. The PBCH changes because of this. So for this, the index is 0, the index is 1, index is 2, index is 3, index is 4, 5, 6, 7. Okay. So if you are transmitting all these SS blocks, for example, for index 0, for the SS block 0, what you do is you choose the C in it by placing this 0. Okay, and generate the DMRS and send it off. Okay. For the SS block 1, index 1, you change this to 1 and transmit it. SS block 2, you change it to 2 and transmit it. Okay. So at the receiver, once you get you lock onto one of these SS blocks at the receiver. Not all, now you will lock onto one of these things. Okay. At that point, suppose you lock onto 2. First, you then regenerate your DMRS and trying to find out what index it is, so that you know the timing location. Mr. Vijay, does it make sense?
Yes, sir. But this can be intercepted by anyone, sir, because this is a known.
This is intercepted by anyone. This is broadcast information.
Okay.
Okay, this is not for any particular UV. This is broadcast information. You're just transmitting SS blocks. That's all.
Yes.
Okay. So in this case of 4, ISSB is 3 bits now. So what they did was they multiplied by 4 NHF. So the last 2 bits are occupied by SSB, and the next bit is occupied by whether you're on the first half frame or the second half frame. Okay. So once you decode your ISSB, which is 3 bits, okay, what happens is the 2 bits will be SSB index, and the other 1 bit will be which half frame you are in. Okay, so for the 64 case, you get only the last 3 bits. The other MSBs, I'll tell you in a minute. Okay, this is how they use the DMRS to, use the correlation in the correlate the DMRS sequence to understand which index of the SS block you have transmitted. Fine. Any other questions before we proceed?
So what is the location of this DMRS? Is it part of PBCH or where?
It's part of PBCH. So PBCH, this part of the PBCH, the location for the DMRS is given here. It's there in the 1, 3rd symbol and the 2nd symbol. Let's just look at the first symbol, 1 and 3rd symbol. Okay. 1 symbol 0, 1. In the first symbol, it is located at 0 plus V, 4 plus V, 8 plus V up to 236 plus V, where V is N cell ID mod 4. These are the locations, frequency locations of that.
Okay.
Okay, so the DMRS is present in quite a number of places. Okay, so the DMRS sequence will be filled like this. So essentially, what will happen is the DMRS sequence will be filled like this. Okay, we'll get into DMRS in great detail later, sir. For now, what we have to understand is that the index, the OFDM symbol index, becomes part of the random seed generator for the DMRS. Okay. I also put the DMRS location here also. Okay. So how many bits are there for PBCH? Okay. It turns out the number of REs for PBCH. Okay, so this is the 0 first OFDM symbol. Second, I mean, if you start at 0, this is the first and the third OFDM symbol. For the second OFDM symbol, you have half small parts, 48 plus 48. So there are 576 REs that are there for PBCH. Okay, and the number of DMS REs are 144 in the PBCH block, in the SS block. Okay, so if you 576 minus 144 is 432 RE that are there for data. And you use QPSK modulation for PBCH. So 432 into 2 is 864 REs, 864 bits can be done in PBCH. Okay. It turns out that the actual message bits, MIB message, not MIB message, PBCH message. The PBCH message is 32 bits. And there's a CRC of 24 bits. So effectively it is 56 bits. So these 56 bits are encoded into the 864 bits. Okay, by using polar encoder and rate matching. Okay, effectively the code rate is 1/15, 1/15. Okay, so there's a lot of redundancies built into MIB, so that it's decoded correctly even at low, very low SNRs. Okay, that's what I want. I put this slide mainly to emphasize that the PBCH message, what is there in that, including MIB, is very heavily encoded. Actually, so the redundancy is about 1/15, which is huge, very low rate code. Okay, so let's understand what is there in this MIB now.
So before that, if you can just explain the concept of rate matching here.
So rate matching, what I will do is we'll do this in detail for PDCH. Okay, it's so essentially rate matching. What they do is, and in short, I'll just give you 1 minute brief on what is rate matching, and we'll do this in detail when we do the FEC. Okay. So what happens is you have bits. Sorry, you have your bits, input bits. These are fed into an FEC. Okay, FEC. So generally, this FEC is a constant rate FEC. So for example, it can for LDPC it will be 1/3 or 1/5. There are two options. I think for polar it is 1/9 or 1/8. I don't remember it exactly. Okay. So what this means is, so if you send, let's just take the example of 1/3. Let's take the example of 1/3. Okay. So suppose you send 10 bits, you get 30 bits out. Okay. So 10 bits in, you get 30 bits out. Okay. But I mean, so this is constant. Suppose, but suppose you want a rate half, rate 1/4. Okay, suppose by some MCS table you chose rate 1/4. Okay, you want 40 bits. What you do is you put this 30 bits in a circular buffer. Okay, you start at bit 0 and bit 29. Okay, you put 0, 1, 2, 3 in a circular buffer. Okay, then effectively what you do is you start reading like this, go back and circle until you read 40 bits. Okay, this is called rate matching. So effectively what you are doing is, while your FEC is working at a constant rate, you are repeating the bits that you are transmitting. That's rate matching. So instead of 1/4, suppose you don't want to transmit 30 bits, but you want to transmit only 20 bits. Okay, because you don't have so many resource elements. Okay, then what you do is you start at this point and read 20 bits. Okay, so you're matching the effective rate to whatever rate you want, and the rate and the number of resource elements that are available. This is called rate matching. Okay, this is very short introduction. We will do this in very great detail when I do the FEC. Okay, So because your FEC operates at a constant rate and the input block sizes are also kind of fixed, what happens is on the output side, you try to put more parity bits or less parity bits depending upon how much you want. Okay, there's a very strict procedure for this. I'm just showing an example. Okay, that's called rate matching. So what happens here is there's, I think, 1/9 or something is the rate of your polar encoder. So this 56 bits are converted in 56 into 9 bits come out of the polar encoder, and then they do rate matching so that you get 864 bits. Okay.
Okay, right.
I will tell this in very great detail. We'll go into this rate matching. Okay. So what is the master information block that is there? Okay, so this is called MIB message. Okay, so this is the first message that your UE is going to decode. Okay, so this MIB is of 24 bits. How? I'm just showing you how these 24 bits come into picture. The first thing is there's a choice. Okay, you can either put MIB or something called message class extension. I don't know what that is. Okay, so this is one. This choice gives you 1 bit because it's a choice parameter. You can choose that on the top is 1 bit. Then it also has system frame number. Okay, if you look at system frame number, it's a frame number. I told you the frame number is 10 bits. It goes from 0 to 1024 or 1023. Okay, so only 6 bits are present here. The system frame number MSB 6 bits are present here. Is it MSB? MSB bits are present here. Okay. Then there's something called subcarrier spacing common. So this is the first time in which the subcarrier information comes into this. So the subcarrier spacing common is the subcarrier spacing for PBCH and the SIB messages that you're going to decode later, core set 0. Okay, so it's either 15 or 60 kilohertz, or you can do 30 or 120. So it's only 1 bit that's allowed. Okay, so you choose this one or this one. Okay, we'll understand how is this used later. And this is SSB carrier offset. Okay, remember this SSB. What is this? SSB subcarrier. So SSB subcarrier offset is nothing but KSSB. Okay, this is a KSSB. Remember what was KSSB? KSSB was this. Okay, so it allows for 4 bits. KSSB was 4 bits, but you may require 5 bits, where we'll see what happens to the 1 bit later. Okay, that is KSSB. DMRS type position. Okay, this anyway, this again we'll see when we do SSB, when we do later. Okay, something called PDCH config SIB1 message. Where is SIB1 message there? Okay, there's something called cell bar. And some other things which are of not so much consequence at this point. So if you add all this, you get 24 bits. Okay. So what does the PBCH message consist of? It consists of the 24 bits of MIB message. Then it also contains the SFN. If you look at the subframe number, only 6 bits are here. You require 4 more bits. The other 4 bits are put outside. Okay, there's a reason why they do it. I'll tell you in a minute. Okay, the other 4 bits are put here. Okay, and there is a half frame bit. So what is this half frame bit? It will tell you which half frame you are in, whether you are in the first half frame or the second half frame. Okay, and the last 3 bits are interesting. Okay, so last 3 bits, what happens is if you look at the L, index L, if you look at the index L, when the 64 index, specifically of the millimeter wave systems, when you decode with the DM-, you get only the 3 least significant bits, but you require 6 bits. So what happens to the other 3 bits? For sub-6, for 120 kilohertz and 240 kilohertz subcarrier spacing, this last 3 bits correspond to the 4, 5, 6 bits of the SSB index. Okay. If it is not 120 240 kilohertz, which is then the sub-6 gigahertz, then this A30, A31 does not mean anything, but A29 is the MSB of KSSB. Okay. So if you look at KSSB require 5 bits. Okay, for sub-6 gigahertz. There's 4 bits per millimeter wave. Out of this 5 bits, 4 bits are coming from this thing. The last 1 bit comes from A29. Okay, so when it's sub-6 gigahertz, anyway Lmax will be less, and this Lmax does not make sense here. You can use the DMRS to get the index there, and you use the A29 to represent the MSB of KSSB. Whereas if in the millimeter wave system, KSSB is anyway 4 bits, so there's no problem, and you use these 3 bits to denote the SSB index.
Sir, you said ISSB also part of this MIB or PBCH, sir.
What? Sorry, can you repeat it?
ISSB, sir. ISSB.
Yeah. So ISSB is what you decode using the DMRS. Yes.
Yes, sir.
So what is the ISSB used? ISSB is used to represent index cell. When you represent the index cell, so for for sub 6 gigahertz, index is, 3 bits are sufficient to represent the index because maximum of eight positions are there. Whereas for millimeter wave system, you require six bits, in which 3 LSBs are represented by this DMRS. The other 3 bits are represented by these 3.
Okay, sir.
Vijay, is that fine?
Yes, sir.
Okay. So, any other question before we proceed? Okay. So finally, when we decode the SS block, that means PBCH also, what do we get? I'm just going to zoom it a bit so that we can see it easily. Okay. Of course, the band you are operating, you know, because of the frequency location. You also know KSSB. Okay, KSSB is that offset, the gap to the offset. For 120 kilohertz and 240 kilohertz, you can decode them using MIB, from decoding MIB. Okay, because this is a subcarrier offset. Okay, 4 bits. Okay, and for the sub 6 gigahertz, you will decode. It's a combination of MIB and 828 bits. Okay, and you get the system frame number, 6 bits from MIB, and 4 bits from PBCH. 6 bits are coming from this thing. 6 bits are somewhere here. A system frame number 6 bits, and other 4 bits are coming from this PBCH. Okay. SSB index. Okay, so for Lmax equal to 4 and 8, you use DMRS random seed to understand which index you are there. For millimeter wave system, you use DMRS to get 3 bits, lower 3 bits, and the PBCH 3 bits, the higher 3 bits from the PBCH, 829, 830, and 831. Okay, so we also know the half frame. Okay, half frame you can either get from DMRS or also from 828. Okay, so for Lmax equal to 4, you can also get this from DMRS. Otherwise, you can also get it from half frame bit. For the other two, Lmax equal to 8 and Lmax equal to 64, you get it from 828. Okay, subcarrier spacing you get. You also get SIB1 information. Next, we'll look at this PDCH config SIB1. We'll look at this carefully in the next coming classes. Okay. Okay. So you understood what all happens. So essentially, there's a reason why only the 6 bits of system frame number are put in MIB. It turns out that MIB changes every 80 milliseconds. Okay, so this is a question I gave here. It says MIB is always transmitted on the BCH with a periodicity of 8 milliseconds, and the repetitions are made within 8. So essentially, what happens, because it's changed with 80 milliseconds. In 80 milliseconds, how many how many subframes can be there? 16 subframes can be there. Okay, so the 16 subframes would correspond to these 4 bits, the LSBs, so that you do not have to touch the MIB message until 80 milliseconds. So you can assume that the MIB message is always constant till 80 milliseconds. The same MIB message will be repeated. The SFN frame number, that's why LSBs are put here, so that the MIB message doesn't have to be touched. If all the 10 bits were put here, then every subframe it changes. Yeah, so every frame it changes. Okay, that's the reason why they split that to 6 and 4. Like that. Okay, so this concludes SSB decoding. So at this point, what do we know? We know the frequency location, we know the time location, we know the system frame number, we know the OFDM symbol number, we know the half frame. So we know a lot of stuff about the system. And what is the subcarrier spacing? It's going to use for course at 0, which is the SIB1 messages. Okay. The next class, what we learn, we look at is what is the information that the SIB1 message consists of, and what is its frequency location relative to PBCH message or the SS block that you have decoded. Okay. So we'll look at that. And once we understand how do you decode the SIB1 messages, we know a lot of information about the base station. And then we will proceed to the PRACH and other things. We'll look at TD also then. Okay. Okay. So thanks everyone. I'll see you tomorrow then, next class. Okay, thanks.